Hello, colleagues and friends. I will talk to you today about reliability assessment of existing geotechnical structures. My name is Timo Schweckendiek. I work at Deltaris, a Dutch research institute in Delft, and part-time I am affiliated to Delft University of Technology. My field of work and expertise is geotechnical reliability and risk assessment, and I work mostly in applied research and development and specialized consultancy. And I have underlined the word applied here because this is very much the angle of my talk. It's about application and how to bridge the gap between academia and practice. I want to start with the why I think our community has something to contribute to the assessment of existing geotechnical structures. I will give you some examples from practice and applied research and development, and I will go into development needs. Before looking into the assessment of existing structures, let's have a look at where design, reliability-based design, is applied to geotechnical structures in practice. And I'm drawing here from own experience. I'm sure some of you will have other experiences too. But in the Dutch context, reliability-based design is applied heavily in the field of flood defenses, like dikes and hydraulic structures, because our safety standards are formulated in terms of acceptable probabilities of flooding or failure. Other applications are in the fields of landslides and hurricanes and natural hazards due to the nature and of uncertainties on the hazard side. Also in the design of hazardous facilities, on the lower right, you have 3 LNG tanks in the port of Rotterdam, for which the foundation needed to be designed to an acceptable probability of failure for the standards that these codes handle. And you see applications in offshore foundations, for example, in the optimization of monopiles. But all these are rather special or extraordinary situations. And it makes sense because if you go reliability-based and full probabilistic, it costs more effort compared to standard designs, of course. But the proposition that I want to bring forward today is that existing geotechnical structures benefit much more from reliability concepts than the design of new structures. And that's what I want to make the case for in this lecture. Let's have a look at the Port of Rotterdam and their portfolio of hundreds of quay walls, existing structures. More than 50% of those quay walls are beyond or approaching their design lifetime of most of the times 50 years. So naturally, the asset management shifts focus from new construction to maintenance and lifetime extension of these structures. Another example from Amsterdam. Besides all sorts of other infrastructure assets that the city has, of course, there is a large number of historic quay walls and historic bridges in the inner city center. You can see the numbers here, more than 200 kilometers of these old quay walls, more than 800 bridges, and these are masonry structures founded on wooden pile foundations subject to bacterial degradation. And they need to be assessed for safety and safe continued use. Because in Amsterdam, we have seen failures like this one, a quay wall failure from last year. This was not a very big structure. Nevertheless, this example reminds us of the fact that the lifetime of these structures is not endless or unlimited. And we've seen other failures of bridges or other infrastructure assets in recent years throughout the world. This example is from the United States. And these failures have also led to the American Society of Civil Engineers making an inventory of, let's say, the infrastructure assets in the US and their need for rehabilitation or reinforcement or replacement. You can see some of the numbers here. The numbers are just huge, and this is just for bridges, but there's also such an inventory for roads, airports, ports, and other infrastructure. So the main reason for looking at existing structures is that these structures get older and they approach their design lifetime, or they're already older than what they were originally designed for. And sometimes failures do occur. So there is clearly a need for assessment of the reliability of these structures and of their residual service life. But there are other reasons to look at existing structures, and that is change of use of these structures. Going back to the Port of Rotterdam as an example, Sometimes the owners of these quay wall structures have questions if larger ships can be moored at these quays, sometimes accompanied by questions of is more nautical depth possible here, which would mean dredging in front of the wall and increase of the retaining height. Other questions could be intensified use in terms of the surcharge loads on or next to the structure, or changes in safety requirements. Another example would be railway embankments. The Dutch infrastructure owner of the railway network, ProRail, frequently is facing questions of the possibility of riding higher train speeds, increasing service frequencies on some tracks and the underlying embankments, and also on using heavier trains. So the question is, can that be done safely? Which means that not just the age of these structures and the, let's say, going beyond the design lifetime is a reason, but another reason is if we want to use structures differently than what they were designed for, or if the environmental conditions change, we also may need to assess the reliability. And we want to do inspection and maintenance for safe operation. And sometimes we need to go into retrofitting or reinforcement. And then there is a need for accurate information in order to have cost-effective asset management of those structures. So this was about the why look into existing structures at all, and also giving you some flavor of the numbers and the size of the problem. But why reliability-based? Why is reliability-based assessment beneficial for these type of structures? Well, the first reason is that design codes are generally not suitable for assessing existing structures. There are several reasons, but one of them being that the target reliability values for new structures are based on different premises than the ones for existing structures. If you build a new structure, the marginal cost for increasing safety, which leads to a decrease of risk, is typically much lower than the investment decision of safely keeping on operating a structure versus removing and replacing it, or starting a major reinforcement operation, which typically leads to lower reliability targets for existing structures if, let's say, life safety can be still guaranteed. But from an economic point of view, that should be lower, also accompanied by lower partial factors. Another point is just experience, because if you start analyzing existing structures with the criteria that we have for new structures, you would largely consider them as unsafe, while you see that they're functioning well and that you have, let's say, performance observations of the last decades maybe without any big problems. So there is a contradiction there oftentimes. Another reason is that we have more data on existing structures. We may have inspection data on, for example, degradation properties like corrosion, or other types of degradation like bacterial degradation of wooden structures. And we have data on the performance of those structures, which I call here performance observations. So which could be the fact that the structure was successfully built, so the survival of the construction stage may contain some information. We may have measured displacements of the structure during construction, but also in operation, and we may have other monitored responses to operational loading. And all this extra data that we have on existing structures compared to new structures screams for Bayesian analysis to exploit those data, reduce uncertainties, and make a much more tailored assessment of the existing structures. And if we can do Bayesian analysis in a probabilistic fashion, we can do a reliability-based assessment and hence a more tailored one. So this was about the why, reliability assessment and existing structures. And let me give you some examples from applied research and development that we've been doing recently. First, the bridges in Amsterdam, the historic bridges, masonry structures on wooden piles subject to bacterial degradation, often 100 to 200 years old. And the question there is, what is the residual service life, and how do we deal with the sparse inspection data? The inspection data are scarce because they are difficult to obtain. The wooden piles are under the water, Oftentimes divers are needed to measure the pile sizes, to measure the degree of bacterial degradation of those piles, and that is costly and time consuming. And oftentimes you do not have the as-built data from the archives because the structures are simply so old. The good news was that Amsterdam had already a large database from all those measurements that they did on the bridges. Here I give you an example of the pile top diameter. Right? These piles are bigger at the top than at the bottom because they're like inverted trees. So the top diameter measurements of all the bridges that Amsterdam had are represented in this histogram. And you see that they're ranging quite wide, between 150 to 350 millimeters. So if you go to a random new bridge where you don't have any archive information or as-built information, you would have a large uncertainty in pile diameters. But if you have a closer look into this data set, you see that the histograms for individual bridges, which are indicated here by different colors, are much narrower, so the variance within a bridge is much smaller than the overall variance of piles in Amsterdam. And it makes sense because just bigger bridges, sometimes with bigger loads, were built with bigger piles and vice versa. So to exploit that information, we developed a Bayesian model for the Amsterdam situation on a couple of these measured parameters, like the pile top diameter and the thickness of the degraded layer. And I will just treat that here conceptually, but we always have sort of a mean value that is uncertain for an individual bridge, and we have a variability component within the bridge, a variation, for example, of pile diameters, and together these form the uncertainty in an individual pile. So from the database, we could establish prior probabilities, and then if you have some data points on an individual bridge, just a few of these measurements allow you to use Bayesian updating and get an update on the bridge mean and also on the individual pile distribution. And we could use these distributions and other uncertainties in a Monte Carlo simulation. I'm showing you this picture here. Don't try to read it. It's all in Dutch, just to give you an idea of the number of parameters involved. Some of them are on the geometry of the pile and the degradation properties. Others are on the pile-soil interaction. And it allows us to sort of simulate a model of the forces and stresses over depth in the pile, including uncertainties. The stresses in the pile, in Eurocode terms, are sort of the effects of actions, which we determine by Monte Carlo simulation, and then we obtain a distribution like the red one here. Now, from that distribution, we can extract or determine an assessment value, EA, where the sub A is for assessment as opposed to the D that you're used to for design, at a certain exceedance probability. And that exceedance probability is based on two components. One is the target reliability index, beta T here, and the other is the influence coefficient of the effects of actions or the stresses here. So the alpha E would be the form influence coefficient if you did a fully probabilistic analysis. We based this here on the recommended values in the ISO 2384, but are now in the process also of calibrating these values. Now, once you have that assessment value, you can compare that to the resistance or to the material strength, in this case the wood strength, in order to make your assessment and determine a unity check value, which is the inverse of the factor of safety that the structural engineers use. Why did we just go semi-probabilistic and not probabilistic here? Because there was a lot of discussion on how to probabilistically model the wood strength. So we said, let's just take the value from the standard here, the assessment value, and then do the part that we can do probabilistically and better, let's say, incorporate the uncertainties at hand on the effects of action side, fully probabilistic. So what we have ultimately with Amsterdam is that we establish a priori probabilities based on their database, add inspection data, do Bayesian updating, which leads to optimal use of available data, both the regional and the local ones, and with the Monte Carlo analysis, and which I didn't mention, but which includes also averaging over piles, which is much easier in the probabilistic analysis. we can determine an assessment value, and which leads to a less conservative assessment, more tailored to the uncertainties at hand, and which still is within the framework of the Dutch Code for the Assessment of Existing Structures, which is an add-on to the Euro Codes for New Structures. Another example are steel retaining walls along waterfronts subject to corrosion. And the key problem there is that the reliability, of course, in time is negatively influenced by degradation, in this case corrosion. And on the other hand, we have proven performance information. So the survival of operational loads year after year reduces uncertainty and has a positive effect on reliability. Our conclusion when we looked at design codes was, again, that the current codes were not suitable for assessment of existing structures, and mainly because the interplay of degradation and proven performance, which was not taken into account. And if we wanted to do that, we felt the need to go for a time-dependent reliability analysis to look at the development of reliability in time and also be able to derive partial factors. So here's an example from a combi wall, tubular piles with sheet piles in between, where you see the development of the reliability index in time. And here you see that it would the reliability index would drop from construction 4.5 to around 2 in about 90 to 100 years' time. Now, if you do account for the proven performance effect, the survival of the structure, you see a different picture. And if you compare that to the typical target reliability values that we have in our code, you can extend the lifetime from roughly 50 years to 75. So you gain some lifetime of roughly 25 years. So what is the main difference between the purple and the blue curve here? In the purple curve, we would just do let's say, a reliability analysis looking into the future, into a given year, with the uncertainty of, or in corrosion, for example, at that point in time. While with the blue curve, we would include the information of the probability of failure in a given year and the survival up to that point in time. So survival of all the previous years and all the operational load conditions up to that point. And you see that the reliability goes down much slower and you get that longer lifetime. I'm just highlighting the main principle here. My colleague Mark van der Krocht will provide more details in the session after this block. Another example that I mentioned earlier are railway embankments. The Dutch asset owner of the railway network in the Netherlands, ProRail, has set up a large research program because they have challenges with assessing the reliability of the existing railway embankments under changing use conditions, under changing environmental conditions, but also sometimes just for the current operation. And besides, of course, research more on the solid mechanical sides of things and the train, track, embankment interaction, more on the mechanical side of things, we also will look into some interesting reliability and probability elements to have a better tailored assessment for the slope stability of these embankments. One element in that would be tailored reliability targets. If you look at the general purpose reliability target values from the Euro codes, they were made for buildings and bridges and also for new structures. Here we will look at existing structures and specific risk profiles of, for example, slope stability and subsequently derailing trains and all the consequences after that. We will also look into heterogeneity and spatial averaging. Interestingly, here, the spatial averaging will not only depend on the soil variability, but also in the sort of geometrical configuration of the axles of the trains, the variability in axle loads for the trains, and so on, determining the failure volumes and hence the degree of averaging that you can expect. We will look into reliability-based calibration of partial factors because we believe and see that general purpose partial factors from the geotechnical codes do not really cover well the uncertainties in this problem. And we will look into Bayesian site characterization in order to make optimal use of all the site investigation data that we have in terms of lab tests, CPTs, etc. This is mainly done by my colleague Antonis Mavrotsakis, who already presented at this conference on a similar topic. earlier. So these were some examples that we were working on or are still working on. And in order to get these things closer to practitioners and to practice, I also want to highlight some development needs on things that I think are needed to fully exploit the potential. And I've put these into 5 main categories, starting on the lower left. We need robust methods, things that do not have too many convergence problems, for example, in terms of reliability analysis, etc. We will need best practices, like good examples and elaborated case histories that practitioners can follow with confidence. There is work on the side of tools and software to lower the bar for practitioners to get started. There is certainly a role for education and also for standards and guidelines. And I want to highlight some of these. So looking at education, I think there are 3 main pillars. University education, I think, is very important. It seems to me that this is also one of the main differences in terms of acceptance in different countries of reliability-based and probabilistic techniques. We have a very good acceptance of these techniques in the Netherlands, and oftentimes I'm asked why I think that is. But if you look at the university education in the Netherlands and at TU Delft, for example, probabilistic design and structural reliability concepts have been part of the standard and compulsory curriculum for civil engineers for more than 30 years now. So people in the field now are trained in these techniques, and it's nothing special or extraordinary to them, but rather normal. Short courses like the ones at these conferences are very valuable, I think, in giving practitioners an idea of what the potential of these techniques is and giving them some basic concepts. But another pillar I think that could be expanded is professional education, targeted at junior and media professionals to extend their toolbox. We have something like that at Deltaris, an annual course that we give on geotechnical risk and reliability analysis. And we provide some of the basic fundamental concepts, but also go quickly into practical exercises. And we see that practitioners are able to pick up then and use these tools in practice, because they come back to us with questions later on. So this may be an element where we can, which can still be expanded in order to get some traction. In terms of tools, I think user-friendly software is important. There are a lot of very good and extensive open source libraries out there on all sorts of topics like probabilistic analysis, reliability analysis, Bayesian analysis. At the same time, these may be limited to the, let's say, people comfortable with programming and scripting out there. But if you want to, let's say, reach a wider audience of practitioners, I think things like the probabilistic toolkit that we developed at Deltaris, it's freeware, so I'm not feeling guilty to mention it here. It can be downloaded, the mentioned link here, but will be very helpful, I guess, because we have an intuitive user interface. You can, it includes all sorts of reliability and probabilistic analysis techniques, and it can be coupled to or interfaced with a lot of geotechnical software. With numerical analysis software, and also with your own models, for example, in Python scripts. And we see that this really helps practitioners to get started earlier if you don't have to go into the scripting first. In terms of research, as I mentioned earlier, I think the big difference between existing structures and new structures is the data availability. And if we want to exploit those, we can still make some progress, I think, in making Bayesian analysis more practically applicable for data-driven site characterization, for parameter estimation in terms of combining in situ testing data, lab testing data, but also in including the performance monitoring data from the structures and inspection data in order to overall reduce uncertainties and really make the difference in sort of a good tailored assessment of a structure. In terms of standards and guidelines, I want to mention Eurocode 7. Eurocode 7, for the first time, will include the mentioning of reliability-based methods as a verification method of limit states. But Eurocode 7 will not include sort of details on how to do that. So there was a need for a guideline. and I am honored to be the convener or the chairman of the task group developing this guideline, in which we have the objective of providing guidance for this full probabilistic reliability-based verification for geotechnical structures. It will be published as a technical report by the Joint Research Center of the European Union, ideally at the end of 2023. And here I have a glance at the tentative table of contents, which includes the reliability verification procedure, the steps that you have to take, some material on reliability targets that you could use, how to characterize uncertainties, not just on the soil properties, but also on model uncertainty, etc., on how to practically do the reliability analysis, and some material on Bayesian updating and partial factors. And I really believe that these kinds of guidelines and anchoring these concepts and standards will be needed for practitioners to actually use these techniques, because they need some legitimacy when approaching clients and authorities. Because if you don't have any sort of authoritative documents to refer to, it's very difficult to get these to get your analyses accepted. So in conclusion, there is definitely a huge and increasing demand for assessment of existing structures and also geotechnical structures. And our community, I believe, has a lot to offer, because existing structures are particularly amenable for probabilistic reliability assessment due to the data availability, due to the possibility to make things more tailored. If we want to make the step to practice, there is still some assistance needed. I've gone through that list earlier. And Bayesian analysis can really make the difference by reducing uncertainties, by incorporating all data that we have on these existing structures to increase the effectiveness. So I hope I have made that case for you, and thank you for your attention.